Hello and welcome to Chapter 10.2 from Stevens' Introduction to Statistics, the Think Anew book. In this chapter we're going to explore linear regression. And in the last chapter we did correlation, where we had a scatter plot, right, that looked like this. For cricket chirps and temperature, or scatter plot for the relationship between demand and price. Right. Okay. So, what linear regression does is say, all right. So suppose we have a significant linear correlation. That means the data follows a line pretty well, and the regression equation is the line that fits it the best. What is that line that it's following? What is the best line that matches this data? So linear regression is all about that line right there. Right. And because it's a line, we actually have an equation for it. And so the line looks like that. Y equals mx plus b. If you recall your equation for a line, there's a slope and an intercept. M is the slope, b is the intercept. Just like this line over here, it has a slope. Y equals mx. The slope is negative 102.61. Plus b and a y-intercept, which is 1490.2. Right? So these are the regression equations. And we will leave it up to software to determine these regression equations. Right? And so here's the regression equation down here where I officially introduce it. And basically, I describe it like this. Instead of y equals mx plus b, I have y hat. And the reason I use a hat in there, and here it is down here. So here's the regression equation. The reason I use a hat over my y is that these values here, the data in this plot, the data in this graph, these are called the x and y's. So the data, so y is already used up with the actual data values. So the y hat represents sort of the predicted value of y given a value of x, right? So it's not necessarily going to occur, you're not going to hit that point with this equation, but you'll hit what is the estimate to y given this value of x, right? So you'll get that point there when you put in this value of x, right? So this right here is y, and this right here is y hat, right? So these should have little hats over them. I couldn't get that to happen in my software that I created them with. So they should be y hats. Okay, so that's the regression equation. It describes the line that best fits the data. And in the sense of best fit, what I mean is if you take all the errors, it means all these little errors here, if the difference between y and y hat, there's this distance, that distance, that distance, that distance. If you take all those distances, square them, add them all up, then the line of best fit has that error. The sum of the errors squared is the smallest. And that takes a little bit of calculus to do, but it's pretty easy if you have software. Right? And so I will give you the regression equation in these. You will not have to calculate it. But it's done through calculus, and it's a optimization. You're minimizing a total error. But software, any software will calculate the regression equation. And you can see examples at stevenstats.com. So the popular misconception is that you will hit every value of y for a given value of x. Right? So what the popular misconception is that if you look at this, if you have some point on your curve, say this point here is 71,98. So the misconception is that if you put 71 in here, you better get 98 here because that's one of the data points. But as you can see, the line doesn't go through every data point. So it's not very often that you'll actually hit a data value, a y value from your data, given the corresponding x value, right? So there's no restriction that that line goes through every point. It just goes through them all with the least amount of error. Right? So that's a popular misconception. So don't be thrown off by that if you put in a given value of x and the value of y that comes out doesn't match up with the data. It probably won't. Predictor and response variables. And again, while the correlation does not guarantee a causative relationship, we as humans, we tend to infer such a cause and effect relationship. And if we decide to do this, there is some conventional structure and terminology involved, right? The x-axis down here, that should be the predictor variable. It is also called the explanatory variable or the independent variable. And the y-axis, the vertical axis, is called the response variable. So this is really the cause, and this is the effect. All right, cause, effect, or the variable that's affected. Right? It is also called the dependent variable. So if you believe there's a cause and effect, you should make the causal variable, the predictor variable, the x variable on the x-axis. Okay. So let's take a look at these things. Suppose you were to collect the data for each of the variables described below. You want to make a scatter plot. Which variable would you use for the predictor variable, which for the response variable, and why? What would you expect to see in the scatter plot? Discuss the likely direction, form, and strength. Right. So in case 1, I have the test scores from test 2, and the scores on the final exam. Right. And we'll put this over here. Which would you put as the x-axis, the predictor variable? Well, I would put the scores from test 2 here as the causative variable. And not because first off, doing well on test 2 probably would cause you to do a little better on the exam. But specifically, it happens before the exam anyway, so it's certainly impossible for the score on the final exam to cause you to do better on the test 2 because test 2 happened first. So I'd put the final as the y-axis. Right, you'd expect, doing well on test 2 may not cause you to do better on the final, but certainly if you do better on test 2, you're probably going to do better on the final and better in the course in general. So I would expect a pretty good positive relationship. I could be wrong. There's probably some outliers here or there. Maybe not even outliers, but just variables that don't fit the line very well. Okay, height and weight. And I'm going to erase this one because I sort of don't have room for all of these. So I did height and weight, put them in a scatter plot. What would I put as the x variable? X, y. I think I would expect a pretty strong positive correlation. The taller somebody is, the heavier they're going to be. And I would probably put height down here. Just because being taller, if someone is taller than somebody of the exact same stature who is shorter, the taller person is going to weigh more. So being taller does in fact cause you to weigh more, whereas weighing more does not necessarily cause you to be taller, right? And there's going to be plenty of exceptions to this rule. There's plenty of tall people who are light, plenty of short people who are heavy, but for the most part, the tallness will cause you to weigh more. So I'd expect pretty strong. I might expect sort of clustering for the men and the women, but in any case, I would expect something like that. Of course, there'd be lots of outlying data points. Students, height in inches and height in centimeters. All right, again, I'm going to get rid of here. And is there any reason to make one the causative variable and one the response? Well, being tall in inches certainly does cause you to be tall in centimeters and vice versa, but it doesn't really make any difference which one's down here. But the correlation will actually be perfect, right? Because if you are this tall in inches, we'll put inches down here, and centimeters here, no one is ever going to be this tall in inches and be anything other than exactly this tall in centimeters. And that's the case for all of these. So you would actually get a perfect correlation, and that the line would be the regression would be the line. It's actually the relationship between inches and centimeters, right? It would be the conversion rule between the two. Okay, shoe size and GPA. Which would be the causative we're expecting? Let's put it this way. Regardless of which is the causative, I can't imagine there's a relationship. And so what that means is if you have this sort of no relationship, the line that fits this, if the correlation is 0, looks like that. Just a horizontal line. Some people have proposed how GPA and shoe size might be related. I'm not buying any of it. Okay. Number of miles driven and gallons used. Gallons of gasoline used, or liters of gasoline. Alright, so which is X and which is Y? Which is the causative? I guess from the driver's perspective, driving causes the gasoline to go down, right? So I would say the miles down here, and then the gas used here. From the engine's perspective, it might go the other way. The more gasoline you stick into the cylinder there, the further I seem to go. But from a driver's perspective, the driving the miles causes the gas to get used. And what's this look like? Is this a positive or negative? You know, the more miles I go, the more gas is going to be used. So I would expect, and it depends if this is the same car. If it's the same car, I would expect a pretty close, tight, positive correlation and a positive regression equation. The positive slope on the regression equation. Okay, so now we're going to interpret some of these properties. And remember, our regression equation looks like this. Y hat equals mx plus b, where this is the slope, m is the slope, and b is the intercept. It's the y-intercept. Y-intercept. By the way, what would the slope over here be? The slope. Let's do our little example for miles. What would it be? It would be gallons. It would be gas. Change in y over change in x would be gas in gallons over miles, right? It would be gallons per mile. It's the inverse of the popular miles per gallon, right? And some people have proposed that it's probably better to gauge a car's fuel efficiency by the gallons per mile ratio as opposed to the miles per gallon. But in any case, the slope of this relationship is going to get to the fuel efficiency of the car, right? Okay, so interpreting the slope. The slope of the regression equation predicts the change in y given a unit increase. I'm going to erase this because these are important words. It's the change in y given a unit increase. That's important. It means if you go up by 1 in x, the slope gives you the predicted change in y. In economics, this slope is called the marginal change. All right. Interpreting the y-intercept, the b right here, the regression equation represents the predicted value of y when x is 0. Right? And sometimes x being in 0 has some meaning, sometimes it doesn't. We'll see some examples. But it usually acts as an upper or lower bound on an expected value. Okay, so here's what I mean by that. Suppose we look at number 1 here. Each problem represents a regression equation for the defined variables. Assume the correlation is significant and answer the questions. So we'll let X be the cost of a pair of Nike Air CB3 shoes in dollars. So X is the cost in dollars, and Y is the number of shoes sold, right? So that's that demand curve, price versus demand, right? And the regression equation that we get, Y hat is negative 2.5 X plus 400. So the Foot Locker charges $150 for a pair of these shoes. How many would they expect to sell? Well, that's found by taking X equals 150, putting it into the regression equation. And you get Y hat, that should be a hat, I don't know why it's a tilde, it's negative 2.5, there's your 150, and you get 25. So they can expect to sell about 25 pairs of these shoes if they charge $150. Interpret the slope. The slope here is negative 2.5. And what that means is if X goes up by 1, right, then we expect the predicted Y value to go down by 2.5. That negative is important. So the Y goes down by 2.5. So for every $1 increase in price, they can expect to sell 2.5 fewer pairs of shoes. And this is an expected value, so it's perfectly fine if your expected value is not an actual value that you can obtain. Interpret the intercept. The intercept 400. So by the way, if you look at this relationship, this is what? Price. And this is the number sold. Oops, sold. It looks like this, right? So this intercept of 400, that's this value up here, 400, when X is 0. So in a sense, it does have some meaning. It represents the number of pairs they can expect to sell if the price was set at 0. I use sell in italics because you're not really selling it at that point. But of course, you wouldn't do that, and so it doesn't have a whole lot of meaning, except it certainly puts an upper bound on the number of shoes you're going to want to stock, right? Because according to our regression equation, we'll never sell more than that unless we give them away. The problem is the regression equation probably comes from data well above 0. So you might get the regression equation from here. And the fact is, once X goes below what you've had it, the relationship might be nonlinear. So it might actually fly up there. So this intercept represents sort of an upper bound or a value on Y when X is 0, provided that linear relationship remains valid near X equals 0. Okay. Your turn. Let X be the scores on test 2. That's X. And Y be the scores on the final exam. That's Y. The regression equation, Y hat equals 0.4X plus 52. If you score 78 on test 2, what would be the expected score on the final? Would take 78 and stick it in for X. 0.4 times 78 plus 52 is 83.2, so you can expect about an 83.2 on the final. Interpret the slope. The slope is right there. It's the term in front of the X, 0.4. It basically represents what happens to Y, the change in Y, the change in the final exam grade that occurs from a 1-point increase in the test 2 score, right? So for every increase of 1 point on test 2, you can expect an extra 0.4 points on the final. That stands to reason, right? Okay. Interpret the intercept. The intercept here is 52. It basically represents the expected score on the final if you got a 0 on test 2. And basically it does provide a lower bound on the expected score. You might not, that value might not be there. You know, you might have data here and the regression equation looks like that. So you might not have had any X's down around 52. Or, yeah, so this is X, that's test 2. You might not have had any data points down here, but the intercept is there. So basically, it provides a pretty good lower bound on the expected score on the final. Right. Provided, again, this linear relationship remains valid when X is close to 0. All right. Return. Second one. Let X be the birth weight of a male baby in pounds. Let Y be their weight at age 20. Weight at age 20. Again in pounds. The regression equation, 11.2x plus 92. If you have a 10-pound baby boy, what is the expected weight at age 20? Well, we take x equals 10, put it into the regression equation. We get 204. So if you have a baby that weighs 10 pounds at birth, you can expect that baby to grow up and weigh about 204 pounds by age 20. Right? And that's just an expected value, and it's, there's no reason to believe it's that accurate. So don't make any bets on this, or get overly concerned if you have a 10-pound baby, and so these are not true to fact lives. These are just examples. I don't want anybody taking this stuff home and making rash decisions based on something they learned on a video on the internet, right? Interpret the slope. The slope in this case is 11.2. Right? So what that means, what does that mean? That's a tricky one. So for every extra pound of birth weight, you can expect an extra 11.2 pounds at age 20, right? So for every extra pound of birth weight, you can expect an additional 11.2 pounds at age 20. Interpret the intercept. This is a very strange value indeed. 92, technically that represents the expected weight of a 20-year-old if his birth weight was 0. So obviously it's sort of that's crazy talk, right? But I guess it does certainly provide a lower limit on the expected age 20 weight of any baby boy. So, if any baby boy is born, you'd say, well, I certainly put a minimum weight on his age 20 as being 92. And again, that is only valid if that linear relationship remains when x is close to 0, right? Sometimes you don't have any data when x is close to 0. So if you make speculations about what y is when x is close to 0, we have to assume that linear relationship continues. And that may not be the case. Right? And clearly, with baby boys, you don't have any 0-pound baby boys. But you do have some pretty small ones. So the relationship might, in fact, not be linear. It might sort of, in fact, I'm willing to guess that it sort of goes like this and then flattens out. Right? For the premature babies down here. Anyway, that's speculation on my part. This is a book about statistics. Sorry, I get sidetracked. When to use the regression equation. So the idea of regression is to make predictions about y for a given value of x. And we call the predicted value y hat. But you should only use this regression equation to make predictions when the correlation is significant. Right, so you don't want to use the regression equation. If the correlation is not significant, then that regression equation is not relevant, right? And so to emphasize this point, we're going to use the following conventions, right? If there is a correlation that is significant, we will predict our values of y using the regression equation. If the correlation is not significant, we won't use the regression equation. Our prediction for any value of x will just be the average value of all the y's. Right? So we only use this regression equation when there is a significant correlation. If it is not significant, our default guess for y is always y bar, the average of all the y's. So we're going to do this 3 times in a row, and 3 related problems that ask this question: are SAT scores correlated with college GPAs? Right? Here we look at a sample of 65 students who went to one of 2 colleges. There's College A and College B. We'll let X be the student's SAT score and Y be the GPA after his or her first year of college. And in the third example, something strange happens when we combine the two schools. And this is another example of Simpson's paradox, which we discussed way back in Chapter 2. Okay, so if we look at College A, 40 of the 65 students went to College A. So N is 40. The average SAT score for those 40 students was 1451.3. The average GPA after the freshman year was 2.964. The correlation coefficient, 0.584. And the regression equation, 0.0014x plus 0.98. Is there a significant correlation? Well, we have to check that with the table in the back of the book, Table 4. So N is 40, right? Let's see what the critical value is. To go all the way down here. 0.312. So we have to beat 0.312. If you go back, you see that we did indeed beat 0.312. We had 0.584. So yes, the correlation is significant. If X equals 1500, the best predicted Y value is, and we get that from the regression equation because there is a significant correlation. So we put 1500 in for X, that's this X right here, and we get 3.08. So if you head into that school with an SAT score of 1500, we predict a GPA after the freshman year of 3.08. If you go to College B, there were 25 there, so that equals N. The mean of the SAT scores, the mean of the freshman year GPAs, the correlation coefficient, and the regression equation. Right? Is there a significant correlation? Well, our correlation coefficient is 0.741. We have to get our critical value from Table 4. We go to Table 4. N equals 25. Right there. 0.396. And we beat that. All right. It beats the 0.396 because we have 0.741. So we use the regression equation to make predictions. If X equals 1500, the best predicted Y value, you just take the 1500, plug it into X, and you get this expression, which reduces to 2.06. So if you're heading to College B with a 1500 on your SATs, you can expect after the first year of college to have a GPA of 2.06. And now notice what happens when we combine them. So now we have the College A are these red dots here, right? College B are these green triangles here. When you combine them into one scatter plot, you get this relationship, right? Now the sample size is bigger. N equals 65. Average SAT score. Average freshman GPA. The correlation coefficient is 0.018. The regression equation, 0.00005x plus 2.61. So if you were to graph this thing, it'd basically be a 2.61 somewhere here going straight across. So the regression equation, or the regression line when you have a very small correlation, is very close to horizontal. Okay, so is there a significant linear correlation? Well, we have a coefficient of 0.018. There's 65 in our sample, so we go to Table 4. We're going to go all the way, we're back up here, 65. So we have to beat 0.244, and we're not even close, right? We're at 0.018. That does not beat, that's smaller than 0.244. So there's not a significant linear correlation, right? So if we don't know which school you're going to, and you got a 1500 on your SAT, the best predicted y value, we don't use the regression equation. Don't use the regression equation. And the reason we don't use the regression equation is because the correlation is not significant. So our convention is we will just use the mean y value, which is this 2.687 y bar. So if we don't know what college you're going to, and you have a 1500 on your SAT, the best prediction I would give is 2.687. And basically, that's no prediction at all. I'm estimating you'll be right around the mean of all the students that left your school. Right. So the interesting thing here is called Simpson's paradox, and what that means is that if you look at college A, there's a significant positive linear correlation. If you look at college B, there's a significant positive linear correlation. If you combine them, in a sense, if you average across categories, and when we averaged across categories in Chapter 2, we saw weird things could happen. And again, they happen here too. When we combine these two categories, suddenly there is no correlation. Right? R is about 0. It's 0.018. So our information is lost when we combine the categories. So it's always best to not combine groups or categories together. If you can separate your qualitative variables, such as separate college A from college B, you're always better off, because lumping things together can destroy good information, and then it can also create fake correlations, and the one you'll often see, it can give you like horribly wrong information. So what you can do, here's another example. Like this went from 2 nice correlations to none. But you can also get a case where you have, say, one group here and you get a nice strong positive, one group down here where you get a nice strong positive, but when you combine them, you actually get a negative correlation. So combining categories can not only wreck a good thing, it can create a fake good thing that really doesn't exist. So very careful. Another little piece of Simpson's paradox. I believe that wraps up 10.2, regression. It's been a pleasure talking at you for this length of time, and I will see you in 10.3, a nice short section.